Hi, my name is Logan Hodgson, and I'm going to be explaining thyristors from a semiconductor device point of view. As we get into the introduction of this device, I should mention that thyristors are semiconductor devices that include three bipolar junctions, and this enables them to be exclusively bistable switches. What does that bistable mean? It means it has like two modes that are stable for it. There's the blocking mode, and then there's the conducting mode. And without any voltage applied to the base, or to this gate, actually, it's not going to change mode on its own. The other way it could switch mode is if it was in the on state. It could be turned off by the reverse bias uh, cathode and anode, but I'll get to that later. In this device, there's no gain of the gate signal, so it's purely a binary mode. And since it is stable, it will pull itself into one of the states depending on what its inputs are. So if it's slightly leaning towards one, it's gonna like commit and adjust adjust the levels inside of it, so it will be in a stable mode. If we go on to the next slide. William Shockley at Bell Labs and some others proposed the device in 1950 for development by engineers at General Electric, and then they were the ones that developed the device in 1956. Its precursor, as you can see on the screen, was the Thyrotron, and this was a gas-filled electrical device that would break down at a certain voltage. So if we look at the diagram over here, there's the anode and the cathode on it, and if there was only a small DC voltage source, there would be no current flowing. However, if you increase that current just enough, you would start to get ionization. So a certain gas molecule would lose its electron, and then they would move in opposite directions. The ones with a more negative charge would move towards the anode and create more current on the way. And so with the positive charges going in the opposite direction. So this kind of kept a current going through the device while there was still this applied DC voltage source. And so since this was a device that operated with gases in a glass tube using breakdown voltages, it wasn't the most efficient, nor was it the most nor did it have a great lifetime. As you can kind of see in this device, you can see metallic residue building up on the edges just from a little bit of use. So they wanted to create a solid state version of this, and that's where the thyristor comes in. It was the drop-in replacement for this device. As for getting into the specifics of how it works, I've drawn out the band diagrams for each one, and hopefully that should explain how the device is able to operate the way it does. A little bit of notation, I've created like these blue arrows that represent electrons being added to the device from the cathode, and over here we have the blue arrow representing holes being added to the device through the anode. And so as you can see on the diagram, we have our four doped regions with our three junctions. In the forward blocking mode, starting out with everything is stable, there's very little current since there is a zero bias sorry, between the P and N junctions on either side of the device, between these two PNN. Diffusion and drift current are going to cancel each other out, so there's going to be no net current there. But for the P and N diodes here in the middle, there's this huge voltage potential, and it acts as a reverse biased PN junction. So you're going to see very little current moving from the end of the P. And just as a reminder, this second p-doped region over here is connected to the gate voltage. So as you can see here, since the Fermi level is up here with the cathode, our gate voltage is also going to be at 0. So both our cathode and our gate voltage are at 0, whereas our anode is a positive voltage. That's why I wrote the minus and plus. to kind of keep that straight. When we move on to the next mode of operation, we see there is the forward conducting mode. So we look at the anode and cathode. They have the same bias, so which is why it's still called the forward modes. But now we're going to get a little bit of conduction. So at first, we have some drift current that starts to take place. Now that we're adding holes with this new blue arrow, we're adding holes into the second P junction, and then they're going to start drifting over to the cathode, and then electrons are going to start drifting here. Because by setting this this gate voltage to a high voltage, we bring down the Fermi level to this level, which enables the drift current to happen. So we're kind of just pulling that Fermi level down, and which prepares us for the next state. As you can see, there's no longer this big PN gap here. So we're going to see what happens with that next. So now that this P gate has been brought down by increasing the potential on it, we're going to start seeing holes diffuse into this N doped region. And remember, there's no gate attached to this N, so nothing is going to keep the Fermi level at a constant level or anything. It's just going to start rising as electrons diffuse out of the device and holes diffuse into the device. It has no reason to replenish these electrons that are up here. Nothing is going to keep it up at that, or nothing's going to hold it down at that high voltage. Yeah. So so all the holes are being provided from the anode and electrons from the cathode over here. The main source of current here is this drift current, as electrons kind of tumble over this potential, and then holes like tumble up that potential, or down the potential for them. Everything's downhill with drift current, but they're gonna be annihilated as soon as they get there. But we're gonna see some rebiasing of these regions. Finally, we're in our steady state mode of now we're doing some conduction from anode to cathode, so we can turn our gate voltage off. So it's just going to sit there floating. We could pull it up. That might reduce the current in the device a little bit, so usually it's just no voltage is being applied. So you could think of it as an open circuit, or another floating gate. So we're going to see, if we imagine we're a hole in this first P region, we've been injected from the anode, and we're going to diffuse into this N-doped region, which now has a pretty high Fermi level. So now that we're here, we're going to drift our way down this potential, high voltage, low voltage, and then diffuse into this N-doped region at the end, where we're gonna recombine with a diffusion. With these electrons from electron donors, which are gonna get replenished right away from the source. But by doing so, we're seeing a net electron flow into the device from the cathode. And if we look at it again from the electron's point of view, being injected into the device, if there's no holes down here to annihilate, we're going to move on and kind of diffuse into this P region. And since this gate voltage is just floating there's plenty of diffusion happening here. Keep in mind that these N and P regions are doped pretty small, so it is possible for these charges to totally just drift into this other N region. And that's totally energetically favorable given the low potential of the electrons here. So the electrons want to come down here. So they've drifted down here, and then there's a high concentration here, so they're going to diffuse over here, where they're going to get annihilated with some holes in this p-doped region, which more holes are going to be replenished by this arrow over here. So it's this whole cycle of moving down the device and recombining that really provides the current that goes through this device. All right, the final stable mode. So we've discussed the forward conducting, forward blocking, and now here's the reverse blocking mode. This is the process that happens when the device turns itself off after the anode and cathode kind of switch polarities. So now I'm probably incorrectly calling it an anode since it is going to be the place where the electrons come from and annihilate these holes over here. But it is still like um, where the holes are going to be. They're still the majority majority charge carriers over there. So holes are being drained from the device at the quote unquote anode. I'm just calling it that so we can keep which side of the device is which. But holes are going to be drained. Since these gates were floating, we're going to see lots of drift current as the potential kind of like shoots down to meet, so the Fermi levels will realign up here. So in reality, this will happen pretty quick, especially as the current just falls out. And any currents that happen to flow in here will quickly get annihilated with the electrons, which in turn will like further increase or decrease the potential, which raises the Fermi level up to meet the level of the anode terminal over here. So as you can see, there's no more, once this drift current happens, moving charges from minority charges, and once all the minority charges are either eliminated or have drifted back into where they become majority charges, the potentials are going to be restored, as we see in this next diagram. And so now we see this whole anode terminal is kind of a zero biased transistor. So there's not going to be any net current flowing. I'm just showing these blue arrows still because if there are any excess holes, they are going to be moved out onto the anode side of the thing, and any extra electrons are going to be drained on the cathode side just for any net current. But at this point, there won't be any. We can see diffusion and drift in this zero bias. There's a net zero. Any holes that diffuse over here will be annihilated, and any electrons that move over to the left will be annihilated. Same thing with this next NPN junction, since it's zero bias. It's totally symmetrical down the middle here, and nothing's going to happen. If we look at this PN, we see this reverse biased PN diode. So whereas the original PN diode was reverse biased in these middle two in the forward blocking mode, now we have the reverse bias happening between the second p-doped region and the second n-doped region. All right, I know that was a lot, but hopefully this kind of explains the how this device operates. So in summary, the device, once you switch it on by raising the gate potential while it's in the forward blocking mode, will trigger it to move into the forward conducting mode, and it'll stay on as long as the anode current. So as long as there's current flowing from the anode into the device, it'll stay on. There are certain thresholds that have to be met. When the gate is pulled high, the anode current needs to be at a certain level. Otherwise, it's not going to be conducting because there won't be enough current to kind of rebias those floating gate or those floating p and n doped regions in the middle. So it needs to be at a certain threshold, which is the latching current. And then there's also the holding current, which occurs when which is the minimum current that has to be flowing through the device to keep the current on. So usually the latching current is a higher level, and then the holding current is a lower level. So latching current is a maximum or a minimum threshold for turning it on, but then once it's on, it'll stay on as long as the current does not dip below the holding current. And then to switch the device off, if there's a sufficiently low device, you can turn it off with a sufficient negative voltage at the gate, but this isn't a reliable form of it, and it's not part of the a bistable operation of the device. For the applications of these thyristors, they're typically used in high power situations, like using mains electricity, or maybe a house 120 volt voltage. They're typically best used at low frequency. They don't have great high switching rates, but they're really good at rectifying direct current because they really have this low diffusion capacitance. So you really see in the reverse blocking mode only very small amounts of current moving in the wrong direction, so to say. It's great for instances like motor speed control or even light dimmers. These are great things to use it for. And thank you so much for listening to my presentation. Here are some of my references, and yeah.